Okay, so this lesson is about determining linear and angular velocity, and hopefully you just watched the video before that I made that is about what is linear velocity, what is angular velocity. If you didn't watch it, you should probably go back and watch that first. So what I have here is I just laid out for you the assignment that goes with this lesson. So here it is if you want to do some extra practice problems outside of class and ask questions about it. Now you have that available to you. And actually you can see that I have the assignments that would have went along with lessons 1, 2, 3, and 4. So now you have them all available to you for review purposes. So let's go ahead and grab your foldable, grab your highlighters and things. If you don't have them, I definitely suggest getting yourself some for this class. So the first tab says arc length. And basically, we are going to learn a formula that helps us determine arc length. If you are wondering, what is this thing, arc length? We did talk about it briefly in another video, but whenever you have an angle like this inside of a circle, it creates an arc. And that arc has a length, arc length. And we call it in mathematics S. And even in upper level mathematics, it will always be S. And so I'm going to go ahead and just highlight that, arc length. And that's this part right here that I'm pointing to. Okay, so let's go ahead and look at this formula that I was referring to. So the length of an arc S intercepted by a central angle theta is S equals theta r, where r is the radius and theta is in radians. Whoa, okay, let's break that down a little bit. I like to draw a picture, so I'm going to draw a circle pretty similar to what I just drew a second ago. And we're going to draw an angle in here, so I'm going to make it obtuse. We don't know our angle length, so it's called theta. And our radius is right here, and it's r. And then I just described to you the arc length is this outside S. So now we kind of have something to look at. Also, I'm going to highlight length of arc S, highlight my arc here, and then I'm also going to highlight it in my formula, S equals. The next thing we run into in this description, the length of an arc S intercepted by the central angle theta. So let's highlight that, central angle theta. It's this guy right here, and it's also in the formula. Notice the central angle theta has to be in radians. That's important. No degrees anymore, radians. And then the last thing that we need to highlight is our radius. R is the radius. It's in our formula, and it's also in our diagram. Okay, so it's a pretty straightforward formula. The arc length is equal to the radian measure times the radius, which this should be familiar because a couple years ago, or maybe last year, you did this in geometry. Okay, we calculated arc length in geometry. And basically, this formula is taking a chunk of the circumference. Okay, and I digress. So I won't go too much more into that. But basically, you know that a full circle has a circumference that's 2 pi r. And by just multiplying by theta instead of 2 pi, we are multiplying by that chunk only instead of 2 theta, which is the entire thing. If that makes sense, awesome. If it doesn't, no big deal. It's just some math understanding that I'm trying to develop there. So let's look at our example. A circle has a radius of 10 inches, and just for the sake of fun highlighting, I'm going to highlight that radius of 10 inches so we have the pink portion of our formula, and contains a central angle of 120 degrees. Now I just told you no degrees, so we're going to need to convert that into radians. Also, it says determine arc length. So we need to figure out what arc length is. So the S is what we're looking for. And then we have, or we're going to have, theta and r. First, let's find theta, because we have degrees. So 120 degrees. How do we convert that? Hopefully you remember. Use the conversion of pi over 180 degrees. And remember, radians is the invisible unit, so we're not going to write it anymore. So now when I convert this, I just have to say what goes into 120, 180, what can I cancel top to bottom here? Well, hopefully you all notice 60 goes into both of them. So 120 divided by 60 is 2, 180 divided by 60 is 3, and we get 2 pi over 3. That's our radian measure. So now we can say S equals 2 pi over 3, and we already have our R just given to us. It's 10 inches. So our arc length is 20 pi over 3 inches. Remember, when you multiply with fractions, you just go across the top, across the bottom. That's how I get this 20 pi over 3. And you can also approximate that. If you use your calculator and you approximate, I like to approximate to the hundredths, and you would get 20.94 inches. If you approximate, you have to use the approximating symbols. Okay, so that's finding arc length. There's two other things we're going to do in this lesson, though. We are also going to be finding linear velocity and angular velocity. Remember from the previous video, linear velocity is distance over an amount of time. Angular velocity is how many times you go around a circle in radians per time. And I have this little definition here that linear velocity is the measure of linear displacement of a particle per unit time. That's the official definition. So if a point is in motion on a circle, its linear speed or velocity, speed and velocity are the same thing, is, and then you've got this formula. Whenever you see multiple equal signs, that just means that the linear speed, which is v, is equal to s over t. It's also equal to r theta over t. The reason why both of these work is because look up here, s equals theta r. So could we just replace s in this formula with theta r? They're the same thing. So I'm not going to go through the trouble of highlighting all this, but if you want to pause and take the time to label each of these, that might be a good idea. Label t is time, r is radius, theta is the angle in radians. You know, if you want to do that, go ahead. So now what we're going to do is look at an example.